Hello, everyone. Welcome to today's webinar, Build Serverless ML Systems with Hopsworks. At ODSC, we're excited to collaborate with the best and brightest in the industry to present to you, and we're happy to welcome Jim Dowling, CEO of Hopsworks, as our speaker today. For those new to ODSC, we're one of the world's largest applied data science and AI communities. We have over 68 local meetup chapters across the globe, as well as in-person virtual conferences in Boston, Dublin, London, San Francisco, New York City, Sao Paulo, Tokyo, and Bengaluru. Please visit odsc.com for more information or join the ODSC community Slack channel to keep yourself in the loop. We will share the links in the chat in a bit. On this next slide, you may find a list of the upcoming events or the one which you are welcome to access on demand with QR codes to their pages and registration links. Feel free to choose the one which you are interested in the most. This November, our team would like to invite you to ODSC West 2022 for expert-led training in open source tools, essential frameworks, and more. And this week, we have a great 2-in-1 offer, and we will share more information in the comment section. A quick point before we get started, you can ask your questions in the tab on your right-hand side. Please be advised the recording and slides from this session will be sent to you within the next 1 to 2 days. Without any further ado, thank you for joining us today, and we're ready to begin the session. Jim, the floor is yours.
Thank you, Ruby. Hi, everyone. Thanks for joining today. So today I'm going to talk about going beyond notebooks to build serverless machine learning systems within using our platform Hopsworks. So we're going to use free serverless systems to build systems, and I'm going to show you what we're going to do. So we're going to build a serverless machine learning prediction service. I'm going to go through a case study. The case study will be about predicting the height of waves at a beach. But what the platform I'm going to build will consist of are what we call feature pipelines for creating features, and they'll be run by Github Actions. So they're going to be actually notebooks. So we're going to use notebooks to implement our code, but it's going to be a full serverless machine learning system. So we'll have notebooks running once a day to create features. We'll have notebooks making predictions twice a day. So it's a batch inference pipeline running twice a day. We'll have a notebook to train a model. That doesn't need to run on demand every day. It can be run when you need to run it. So when you collect more training data, you can run your training pipeline. But maybe in a production system, you might want to schedule it for execution as well. And then finally, a prediction service or some sort of serverless machine learning service should provide some output to stakeholders. So there should be some user interaction. Either you're making a service more intelligent or you're providing some predictions to users. In this case, we are predicting the heights of waves at a beach. So we can do that with a PNG file. So just an image showing the graph of predictions. And it will be a GitHub Pages account. So the only thing you'll need to do to follow along here, and the code is available. So if you want to go to CJ Surf on my GitHub account, Jim Dowling, CJ Surf, you can find it all. It's all open source. And if you want to jump into the code, you can do that straight away. The only thing you'll need to follow along would be a GitHub account, which many of you will already have, and also a Hopsworks account. So you go to app.hopsworks.ai to get started. So the title of this webinar is Beyond Notebooks, and you might think, what does that mean? Well, it means we're not just training a model, evaluating a model, and then saying we're done. So in a traditional course where you look at or you learn how to do machine learning, you get a static data set. So you might get something like the iris flower data set, or you might get MNIST if you're doing deep learning, and that data you'll download. And maybe it's from a URL, or maybe it's from scikit-learn or TensorFlow itself, because they have support for these standard data sets. And you never have to do any feature engineering, really. The data is ready, it's prepared, correct, and unbiased. And then finally, once you've trained your model, you'll evaluate your model on some test data to check to see your model generalizes. And that's basically the way in which you communicate the value of your models. So I don't think this is how we should be doing it these days. We've moved beyond that, those capabilities in lots of platforms, and you know, there are user interfaces you can build around now, even in Python. So I'm going to use GitHub Pages today, but you could just as easily use Streamlit, which is Python-based user interfaces. And there's also Gradio, which is a plugin to your notebooks that does the interactive user interface. But apart from the user interface, the main difference between a production machine learning system and these courses where you just work with static data is that data never stops coming. Now, if the data never stops coming, you need to have some way of taking that data and turning it into features that you're going to use for training and also for inference. The data may come from many different sources. We know the cliches that most of the work is cleaning up the data and making sure you have good quality features. You do have to write code typically to extract your features, validate the features. And I mentioned already, you should communicate the value of your model with a UI or service. And then finally, once you've built a prediction service, you need to make sure that it runs reliably. And if you want to make changes to it, so you want to change the features, you want to change the model, you want to have different training data and train a new model, well, you're going to have to do that with support, with system support for doing that. So things like versioning of your assets, your features, your trained data set, your model, testing those assets to make sure that they work reliably, and also then upgrading and downgrading if you need to when you want to put a new asset in production. So I'm going to start by saying, what does beyond notebooks mean? Well, the classic machine learning pipeline, you might have heard the term machine learning pipeline. A machine learning pipeline is a very kind of generic term, and typically what people mean is a monolithic pipeline. That means a pipeline that goes all the way from your raw data into the features. It turns your raw data into features, trains a model, and then evaluates or scores your model on some test data, some holdout data it hasn't seen before. And often you'll do this in a single program. And many data scientists will do this in their work. They'll get a dump of data from a data team. They'll write a monolithic ML pipeline and show that they can solve a prediction problem. And then they might hand that that notebook over the wall to an operations team and say, please try and productionize this. And often what you'll find is that there's a conflict between the different teams, because the operations team and the data engineering team think that this is not the way in which you should structure your programs, because this won't run in production. And they're correct, because there's no easy path to production, and monolithic ML programs are not an easy path to production. So we need to break this monolith, and we'll see how we're going to do it today. So the way we're going to do it so that we can run it as a serverless system, and by a serverless system, I mean a system that will run without any servers. I won't need to install software. I won't need to upgrade or maintain any systems. I'll just be able to run Python programs, in this case notebooks, and the infrastructure will just be a web page that I use to interact with it. In this case, GitHub and Hopsworks. So this is a serverless machine learning system. We're breaking up the monolithic pipeline into 3 parts. We're breaking up into a feature pipeline, which will take our raw data. So we've got our raw data that we called raw data in the previous slide, but now we've broken up into 2 parts. The first part is what we call backfilling data. So often when you want to train a new model, you may have some historical data. It's in your data warehouse or data lake, and you'd like to take that data, create features, and train the first version of your model. But if you're building a production system, new data will always arrive. Maybe you're predicting a propensity to buy on an e-commerce site. Maybe you're doing predictive maintenance on some system, but new data will always be arriving. So you want to make sure that you use the same feature pipeline with both historical backfill data and new data. The second part, once you've created your features and you have pipelines that are going to keep running to create your features the whole time, is that you'll need a training pipeline. And this training pipeline can be run on demand. You can run it on a schedule if you want, but that's up to you. But basically, it's going to take all the new training data that has arrived in the period of time that you want to use to train with. Sometimes models will use all the historical data. Sometimes the models become stale quickly, and you want to use a short time window of training data to train your model with. And once you've trained a model, you need to make it available. That model that you've trained, you need to make it available for inference pipelines to make predictions with. So the model typically will be registered with a model registry. And today we'll look at using Hopsworks as the model registry. There are other model registries out there like MLflow, Weights and Biases, but they're very simple services. They really just store versioned models and artifacts around them, and you're able to register them and download them. And you want to do that securely and in a high availability way. So in Hopsworks, you don't need to install anything. You just use it pip install our library, and then you can use the feature store and the model registry. You don't need to install anything. Now, the last part of our pipeline that we've broken up the monolithic pipeline is what we call the inference pipeline. So that's the pipeline that's going to make predictions with new data. So it's going to take new features. In this case, it's going to take them from the feature store because they've already been created as features from the feature pipeline. And then it's going to put some output. So the output will be predictions. Today we're going to look at images that we output, which are the predictions in graph format. But you can, of course, have dashboards, and you can have outputs to operational systems that make predictions on behalf of users. It's a very flexible way. Now, just a point of order at this point. If anyone wants to ask questions, you can just write them into the webinar, GoToWebinar on the right-hand side, and I'll be able to see them, and I can then just pause to answer them. So what we see here is quite a typical setup for a batch inference system. So a batch inference system means it's going to run on a schedule. So every day or every hour, it's going to take new data, make predictions, and output them somewhere. And we'll have the feature pipeline taking the new data. This will run on a schedule as well, the feature pipeline. And the training pipeline, you could run on a schedule or not. It's your choice, really, depending on how often or how frequently you need to update the model, depending on how quickly the model goes stale effectively. So there is another case apart from batch inference, which is when we want to run a model online, an operational model. So it's running, it's making an application that we can see here intelligent by adding intelligent decisions to that application. So the application will issue requests and say, please make a prediction for me. And this online inference system will be able to look up pre-computed features. So some features really around historical data and context data can come from the feature store. So an example of that in e-commerce would be that this online inference service is going to be a stateless service. It won't know anything about your history, and the application will probably also be stateless. It won't know about your prior purchases, but the feature pipeline will be writing the features about what you've bought in the last maybe day or week or month or year. Your level of activity at the store, all that historical data will be in the feature store. So your online inference service can pull out those features to have a better understanding of your buyer behavior. And then there may also be some information that comes in through the application. Maybe you have the session history of what you've been looking at, and we'll use on-demand features there. And together, all those features will send to the model that now needs to run on a network endpoint. So we call it that a model serving infrastructure. And you can predict on the model running in this model serving infrastructure. Now, again, in Hopsworks, we do have support for model serving. It's part of this free serverless platform. So you can serve a couple of models, I think, concurrently in the generous free tier. And there's about 10 gigabytes of storage in the feature store if you're curious. And you can have hundreds of, I think, a couple of hundred models in the registry. So that's enough to build, pretty substantial serverless systems like I'm going to show today. Okay, let's move on. So that's basically where we are. We're going to break up the monolithic pipeline, the ML pipeline, into the three parts: feature pipelines, training pipelines, and inference pipelines. But what we'd also like to do is when we've built these pipelines, because we're building a production system, we want to make sure that the assets that we're building, the features, the training data that we generate by joining features together, we'd like to reuse features, and the models that we train, we want to be able to ensure that they're trusted, that they're versioned, so that means doing things like what we call an ML ops, automated testing, and the kind of testing you might want to do are unit testing of the feature logic, feature pipeline integration tests. You want to validate the data that gets written through them. In Hopsworks, we support Great Expectations as a framework for writing rules to validate your data. So you can write rules such as if there's no missing value, if the range of a value is between two certain levels. So in surfing, I have a rule which says if the wave is lower than 0 feet or higher than 20 feet, well, that's a problem. And then you also might want to test your models to make sure they're free of bias. With a feature store, you can create what we call evaluation sets. So you might say, okay, I have 5 different regions, and I'd like to make sure I'm not biased against people from these 5 different regions. So we can split our test set into 5 different subsets of the test set, and then score a model against all of those 5 subsets that make sure that there's no significant deviation between the model score for the people from the different regions. Okay, and then finally, you can version, in Hopsworks, we can version features and training data and models so that this is the goal of MLOps really, is to have this big red and big green button. So the big green button will just say, I want to upgrade from version 1 of my fraud model to version 2. And if there's a problem, I press the red button to roll back, and that's it. And that's kind of the vision of MLOps, that it should be just that easy to make your online systems you know, upgrade and downgrade if there's problems. Okay, that's a little bit of the background about you know, how MLOps and serverless ML systems put together, and we've looked at this proposed deconstruction or refactoring of the pipelines into 3 different pipelines: feature pipelines, training pipelines, and inference pipelines. Let's look at a case study for this, and this case study is predicting the height of waves at a beach in Ireland, and I'm currently actually in Ireland. And this is based on work I did many years ago, and it was published at a top machine learning conference called ICML. And what we did was we collected some interesting data sets on a beach. So there's somebody in Ireland who every day goes out and measures the height of the waves, so observes the height of the waves at the beach. And then out in the Atlantic, a few hundred kilometers out, there are buoys that are managed by NOAA, the North American, I don't remember what it stands for, but the Northern Oceanic and Atmospheric Association. They have these buoys that make predictions about the height of the open ocean swell. So you can see when the waves are in the ocean, it's called swell, and you can see that they're quite high. But we don't know exactly how high they will be at the beach. So we have observations at the beach telling us how high they'll be. So the problem is actually quite easy to understand. I think we can see that if we look at a wave has a height. So this is the open ocean swell here. It has a height. There's a period of time between the waves. So the amount of time it takes the wave to go from one wave trough to the next wave trough, that's called the period. And then we have the direction in which the swell is coming. So waves travel in a particular direction. Now, and when you get to the beach, you have the height of the surf, and that's what we want to predict. So this is the label or target that we're going to try and predict. And it's not a trivial problem. So if you look on the right-hand side in this image, we can see that the swell is coming in from the north of the top, and there's a point here. And we can see that these swell lines compress. And when they compress, that means that the distance between each wave gets shorter. The period will actually stay the same, so the wave will slow down, but the height will go up. So the height will actually increase. And we can see at the beach, the gap between the waves is longer, and that basically means that the waves are getting smaller. So to be able to predict the height of the wave at the beach, we need to know about the direction, we need to know about the height, we need about period, and you can see this wave wraps around somewhat, but the wave is still 4 times smaller at the beach than at the point. So a data-driven approach is the way to do it, and you can scrape these swell predictions at this buoy out in the Atlantic, and the beach is over here in Ireland. So that's what we have. We have a feature pipeline that's reading from this particular website, scraping out these swells. This is swell number 1, and we have swell number 2 here. And then we have these observations coming at the beach, and you can see it says the wave height was 4 feet. Sometimes it says a max and a min height, and sometimes it's just the average height. And these come out at the same time every day. So when we did this in 2005, we had an old school LAMP architecture to implement this. This was a production system. We just didn't have the money to run it. That's one of the motivations for today's talk. You can run today's system free. Basically, with GitHub Actions, you get 3,000 hours of free compute, and with Hopsworks, you'll get free storage of your features and models. So we could rewrote this system to make it run for free. So back then, we had MySQL, Java to do the basic machine learning, and a PHP web app. So this is what it looks like in 2022 when we rewrite the whole thing in Python. And you can see it's split up into 3 layers. We have a compute layer for serverless. Now we are talking about GitHub Actions today, but if you're writing your code in Python, there are a myriad of different systems. There's orchestrators like Dagster and Astronomer, Airflow. There's a ton of Lambda functions in AWS. It really doesn't matter which one of these systems you use. GitHub Actions is nice because people have accounts and it's free. That's why I'm doing it here. But what you can do is you can also, and the other nice thing about GitHub Actions is you can put in a requirements.txt file. So any Python libraries you're using in your program, you just put a requirements.txt file in your repo, and it will install those Python requirements. And then you can just use, in my case, I'm using a shell script to run the notebooks using a tool called nbconvert. So it's just going to convert the notebook into a Python program and run that Python program, and GitHub will take care of installing the correct libraries for me. So the way that it works is the compute layer will read this data, the new data from the beach and from the swell predictions, and it will insert that data as data frames, Pandas data frames, into the feature store. Now, the second thing that will happen is that we'll train a model, and we can do that offline. We're not running that as an orchestrated surface. You just open up Colab or your laptop with Jupyter, run train model. It'll read the data from the feature store, so it'll read training data from the feature store and write the model or register the model with the model registry. Now, the last part is that you want to make predictions. So that's our batch predict surf program. It's a notebook, and it will download the model. It will download the latest data that it wants to make predictions with. So it's going to take the swell data, the features in the swell data, and then it will predict the wave heights. And its output is basically a PNG file. So what all it's going to do is commit that file to the GitHub repo, and then with GitHub Pages, we can have a look at that. So I think actually at this point, we'll just have a quick look at that. If anyone has questions, just write them in the chat. Let's have a look at the web page here. So this is the web page CJ Surf. And there's a bit of background. You can see a little bit about the beach, where it's located, the architecture here, and a little bit of description of the notebooks and the data sources. But let's have a look at the actual output. So we can see it says here CJ Surf report passing. This is a GitHub action. And then we've swell batch predict. So there are 3 pipelines. Remember, there's the surf report, which is a program that's downloading the surf report every day. And then there's another one which runs more than once per day. So it's the swell batch predict. So NOAA update their predictions every 6 hours. Now I think I'm only running it every 12 hours. So this workflow in GitHub Actions runs every 12 hours, and this one runs every 24 hours, I believe. And they're passing. So that's nice. You need to know this thing is working. And then the actual predictions are just being shown here. So it's not the most beautiful website in the world, but it's quick. And I can see today is Tuesday, and the surf will be 2 feet tomorrow and about 5 feet on Thursday, which is pretty good, but not so good on Friday. So, that looks like it might be worth the trip at the weekend as well, because we've got some swell coming in. And that's basically it, right? So that image will get updated every time this CJ Swell Batch Predict notebook runs, and that's basically the production system as a whole. Now, it's not a very complex one, but you get the main idea that this thing runs by itself. I don't need to do anything. And we'll have a look at the feature store and the model registry in a bit to see where that data is being managed, because we have the compute, but we also need the state. And the state is basically, in this case, 2 things. It's the features and the models. So, and in fact, there is a third piece of state, which are the predictions as well. So one thing that's really nice with a feature store is that in this case, I'm making predictions and I'm outputting an image, but I can also write the predictions back to the feature store so that I can debug my system to make sure the predictions are being look reasonable and to get an insight into how the system's performing. But let's have a look at the feature store, because not everyone, I guess, has used the feature store, is familiar with the feature store. The feature store for machine learning is a platform for managing your features for training and for inference. And the basic idea with Hopsworks feature store, because there are a number of other feature stores, is that Hopsworks is a Python-centric feature store. You can write your feature engineering code in Pandas, and you can write those data frames to Hopsworks. And it's the only really Python-centric feature store available today. And with the serverless option, you don't need to install anything. So you don't even need to pip install a library. apart from Hopsworks library. You don't need to manage any services or connect to any databases. The thing will just work for you. So the basic idea is that your feature engineering, whether it's aggregations you're doing or dimensionality reduction or data validation, should happen before you write your data frames to the feature store. And one of the philosophies of a feature store is that features should be reusable. Now in Hopsworks, when you write your features, your data frame to the feature store, they get stored in a table called a feature group. And those tables are mutable. That means you can keep adding to them, you can append to them, you can update values in them. And that means over time, the data that's available in them will change, right? So if I had done normalization of numerical features when I wrote the data, well, for a given table of features, I would have to renormalize all of the data every time I write it. Because, you know, if I for any given numerical feature, when I'm normalizing it, I need to compute the mean over all the values. And it doesn't make sense, you know, if I'm only writing a small amount of data to re-index a huge amount of existing data in a table. The other big problem with applying transformations before you write to the feature store is that those features now become less reusable as well. So if, for example, I wanted to get training data from the last 2 weeks because I have some sort of time series data and data older than that is stale, well, you know, if I had normalized over all of the available time series data, well, then I won't be able to read part of that because the normalization is only valid for the entire time series, not for that 2-week period. So the solution to this problem, to make features more reusable, is to apply transformations after the feature store. Now, many of you who are XGBoost lovers will say, well, we don't use transformations anyway. We're just going to just dump everything in XGBoost and it'll all be fine. But in any gradient-based learning approaches, which are a lot of models out there today, you do need to smooth your data often before you prepare it for training, and that means applying normalization. So one-hot encoding, min-max scaling, zero meaning, and so on, scaling values. So let's have a look at the abstractions that we provide to make this a bit easier. Now, I mentioned we have these tables of features called feature groups. You're going to write a data frame to a feature group, and you're going to read from the feature store using something called a feature view. Think of this as being a database view. There's no tables created, there's no data, it's just a logical set of features that belong together. So you would say, okay, these are the features that I want to use to train this model, so I'll create a feature view. And with that feature view, you can use the feature view to read data for training models. So you can read that data as Pandas data frames, even Spark data frames, and sometimes files. Maybe you want the data in CSV format, Parquet format, TF record format, and maybe it's too large an amount of data to read as a Pandas data frame, so you get it as TF records in a bucket in S3 or somewhere else. And then your training pipeline can read that data offline. The second part of the feature view is that if you have an online model, a model that's running 24/7, and it wants to read these historical or contextual features, the pre-engineered features, to add to the feature vectors, well, you can do that again by the same feature view. So it's very important then when we're reading the data from the feature view and we want to apply things like transformations, we're consistent between doing it in the training pipeline and in the online inference pipeline. We'll see that in a second. So often you want to do feature engineering in Pandas. So as a platform, Hopsworks supports taking your existing Pandas feature pipelines. If you're creating features in Pandas, you can just write them directly into Hopsworks. So let's have a look at the surfing example again and see what type of feature engineering we have to do here. Well, one thing we had to do was that multiple swells can appear in the Atlantic. We had to pick out the best one for the beach based on the swell window that arrives at that beach. But we also needed to compute or estimate how long it will take the swell to arrive at the beach. So we added a new column called hitsat. Again, it's all in the source code. You can compute that easily enough by multiplying the swell period by 1.5 to get the velocity of the swell. So let's have a look at what the API looks like for this. So we want to get, of course, the height of each swell, the direction of the swell, and the period of the swell. And once we've done that for all of the predictions, we actually have, I think 2 weeks of predictions, hourly predictions. So it's several hundred rows you get of predictions. and that's a data frame. And then we just write that data frame to the feature store. Now, in this case, that's the swell predictions. In this case, on this slide, actually, we can see it's the beach surf height observation. So this is just going to be once per day, we're going to get a single observation of the height of the surf at a given at this given beach. And this is the primary key here is the beach ID, because you may add more beaches in the future. But there's a number of other things that we can do when we create a feature group. We can say online enabled equals true, which means that the features will be available for online serving. We supply a version number, so it could be version 1 or 2 for this feature group. So if we're changing feature implementations, or we're dropping features, if we're breaking the schema, then we'll need to increment that version and backfill the feature group. But if we're only appending a new feature and we have a default value for it, well, then we can actually do that. It's safe to do that, because the new feature will get appended, and then the default value of that feature will be applied to the previous data. So the rows that were in there will get that new column as well, with the new default value. So there's a couple of other things that we do. We want to select a primary key. We'll notice as well that we also have something called an event time. So when we observe the height of the wave, one of the columns is the time at which that happened, and we tell the feature group that this is the event time for this feature group, because later on when we're joining features together, it'll use that information, that event time, to do what's called a point-in-time correct join, ensure there's no future data leakage, and we'll look at that in a little bit. So the first thing we look at again in this feature pipeline when we're writing the features is data validation. Now, Great Expectations has become pretty much the dominant platform for writing data validation rules. And in this case, we can see one rule. Rules are called expectations, and you put all of your expectations into something called an expectation suite. So in Hopsworks, when you create a feature group, you can say for this feature group, apply this expectation suite. And that means every time you write a data frame to the feature group, the expectation suite will be applied to it, and you'll see the results in the user interface of that expectation suite. So in this case, the rule is quite simple. It says expect column values to be between, and it gives the wave height should be 0 and minimum value, and maximum value 20. And we don't tend to get 20-foot high waves on this particular beach. It's not really feasible to have higher waves, so if it's outside that range, it's probably invalid reading. And this is what it looks like in the user interface. Every time you write data, we can see whether it passed the data validation rules or not. And of course, you can set up alerting. You can send an email or Slack message if an expectation is not valid. And that's what this is showing. Basically, you can alert when data Great Expectations rules fail. So I mentioned that one of the ideas of the feature store is to take existing features and select them and reuse them to create training data. And the way you do that in our platform is with this feature view API. So you write to the feature groups in your feature pipelines, but you read from feature views. So to get started, you'll need to basically decide what features you want to include in the feature view. And in this case, we have two tables. We have the search report, which is saying the height of the wave. And in fact, it's a little bit more complex because they sometimes give a minimum and a maximum height, and sometimes they just give a height. So in the first row, we can say they just gave a height of 1, but the next day they said the minimum height was 1 and the max height was 2, and the next day it was minimum height 2 and max height was 4. So we can see an observation time for these beach, and these come every 24 hours. Now the swell predictions from NOAA come every 6 hours, so they're coming more frequently. So we can see that we have a column here when we expect the swell to hit at the beach. So what we're trying to do is you can imagine here, we're interested is, well, what was the height, direction, and period of the swell, and what was the corresponding height of the wave at the beach? And we want to make sure that this hits that time is going to be before the observation time. So this observation time is actually 10 in the morning. It's not shown here, but when we want to join the features together, we're joining the swell height, the direction and period with the height observed on the beach, where we're going to use the observation times for our label, the surf height. That's the thing we want to predict. But we want to make sure that this first row at 2004, the 1st of January at 10 o'clock, that we have the most recent value for the swell height, direction, and period. We don't want a future one. So in this case, it's going to be the first row here. You can see it's going to be a swell height of 1.25, direction 88, and period 9.8. And the next day, we have our observation time. It came in at 11 o'clock on the 2nd, and we can see that the most recent one was the current was this one here, and so on. So we're joining together all the rows to make sure that there's no future data leakage, and we get a point in time correct training data. Now, if you're to do this in SQL, it's very complex. So we have a domain-specific language in Python. You just write Python code. It looks like Pandas. The code that you write is the following. You get this feature group called Lahinch and this other feature group called Swells, and you just select the features you want. You say, well, I want the wave height from my, I want the wave height from this Lahinch feature group. This is the beach. And then I want the wave period and height and direction from the swells. And you join those together. So this query object you can get back as a Pandas data frame, or you can have a look at it to make sure if it looks okay. And if you're happy with it, you can create a feature view from it. So it's not going to copy any data. It's not going to read up any data. It's just going to create the metadata for this feature view. And here we say that the label, the thing we're trying to predict, is the wave height, and the other columns will be the features. You can also include things like primary keys and event times if you need them. But then you'll probably need to drop them when you're training. So once we've got the feature view, let's see how we use it. And the feature view can help us avoid this problem of what we call training serving skew. That if the transformations we apply when we're training our model are different to the transformations we apply in the inference pipeline, the online inference pipeline, then you get bugs. You can get skew between those two different pipelines. So let's have a look. So what we said was before is that we're going to apply transformation after the feature store to ensure that we don't get that we maximize feature reuse, but we want to make sure that it's going to be the same transformation between training and serving. So in this case, the transformation that we want to apply on the numerical features is normalization. And you can see here, if we normalize, well, the RMSC goes up a bit, but it actually improves predictions slightly by normalizing them. They're a little bit spiky, but again, it depends on the model that you use, right? So if you use a model that needs gradient descent, base model, you probably, and you have very spiky, non-homogeneous distribution of feature values across the different features. Well, then you should normalize them. So here's one way of doing it. You can do it with scikit-learn. You can basically say, okay, I've got a min-max scalar, and I'm going to fit my training data with this min-max scalar. And I'm going to save the pickled scalar object. And then in my inference pipeline, I need to read up the same scalar pickled pipeline. I need to make sure I have the same version of scikit-learn as well in my inference pipeline as I had in my training pipeline. And then I can take in the data I want to, in this case it's called test, but the inference data that I want to predict with. And what I can do is I can basically apply the same transformations because this scalar object is the same object that was created in the training pipeline. So you need to ensure consistency between these two objects, and you version them, code review, and testing. In our platform Hopsworks, you would typically deploy them to the transformer objects or encoder objects to you would save those pickled Python files in the model registry with the model version, so that when you download that model and use it in your inference pipeline, you also can download this transformation object. And this is kind of nice because then the model registry manages the problems related to the versioning and making sure the correct transformer object is used with the correct model. It's a little bit more work. There is another way to do it, which we support in our platform, which is what we call online transformation functions. So we have some support in Hopsworks for very popular transformation functions like standard scalar. And you can say, well, I have a standard scalar here and I get it from the feature store, and I'm going to apply it to the height, the period, and direction. And then when I create my feature view, I specify this set of transformation functions. So here we're taking the three features, we're transforming them with standard scalar, and then when I get my training data, when I call fv.trainTestSplit, which returns my training data and my test data as both features and labels, Well, the feature store will apply the transformation functions when after it has read the data from the feature store. So it's actually doing that as implying them as UDFs, so Python UDFs. And then similarly, when you retrieve a feature vector in your online inference pipeline, the feature store knows that it should apply these transformation functions in the client, and that's what it does here. So it'll apply those transformation functions in the client before it returns the feature. So you don't need to worry about managing pickled Python objects between the different training and inference pipelines. Okay, so that's basically the kind of the slides. If you want to try out the platform, I'm gonna show it to you now in a minute. It's called app.hopsworks.ai, and I'll jump ahead one more thing before we do it. There is a course around this called Serverless ML, serverless-ml.org. And you can register today. It's going to run this month, starting end of next week or the week after. And it will teach you how to write these serverless ML systems. So I'm giving the surfing example today, but we'll start a bit easier. We're going to start on Iris. So how to take the Iris data set and turn it into feature training and inference pipelines, how to orchestrate them, and then we'll work on an example based around fraud. So it's going to be a more realistic one. And how do you get your data? Well, we're going to do synthetic data generation, which is a nice way to be able to mimic a real system without having the overhead of maybe connecting to a real system and working with it. So, but we'll do the basics and fundamentals of ML ops, and it'll all be run on free services. And if you're interested, you can go and register now at serverless-ml.org. But let's have a quick look at back at our code here. We didn't look at any of the code. This is the surfing example we gave. So let's have a look at the notebooks. And we can see here that there's we have the surf report feature pipeline, and this particular program is a feature pipeline that will and this is running against app.hopsworks.ai, but you can also install Hopsworks. You can install open source, and if you do, you'll need to work with API keys. It's a bit more work. In this case, for the reading the surf reports, we can either have backfill set to true, in which case it'll just download some backfill data to put some some basic surf reports in your feature store, and you'll also need to backfill then the swells, so you'll have some training data you can train a model with. If backfill is set to false, then what it will do is it'll basically go and download the latest. So this code here is downloading the latest observation of surf height from this website called lahinchsurfshop.com, which is here, this URL here. Okay, now you might wonder, well, how can a notebook set up this? You can see there's a little trick here. What you can do in GitHub Pages and in many serverless compute platforms is you can set environment variables. So in the GitHub action, I set the environment variable backfill to be true, or sorry, to be false, because when I'm running in the GitHub action, I want to get the latest value of observation of the web height, and I want to write it to the feature store. So in our GitHub action, we set this to be false, and I can probably show you that in a second. Probably find it here. And please shout if you have any questions. You can feel free to write them in the right-hand side in the chat. So we look at our GitHub Actions. Here at GitHub Actions, by the way, in case you're curious, it's this button in the middle here of GitHub. And you can see here that I have the surf report one. So this is our surf report GitHub action. And if I click on it, we can see the surf, we can see the actual GitHub action itself. You can see what it's actually doing is it's installing all of the libraries in the requirements.txt file, and then it's running a shell script, and that's basically all it's doing. And it's going to run once per day at the time of 11:11, and that's basically what it's doing. Now, what you can also do here is you can also, I think it's in. Do we have to go back to here? Okay, so in actions. We go back. No, there's a different one called environment. Actually, I'm not sure if it's security. No, it's in the environment. I'm not signed in. Okay, I'm not logged in. I'm on a Mac. I'm a Linux person. I'm forced to use a Mac. So if I was logged in, I'd be actually able to see there'd be another button related to security, and I'd be able to set environment variables. And there you can set your API key for Hopsworks, and also this backfill to be. You set the backfill to be in this case, false. So the way that GitHub action runs is it actually just runs this shell script. So this shell script here, you can see what it does is it just goes into, changes directory to the notebooks directory, and then it runs Jupyter NB convert. And what this will do is convert my notebook into a Python program and just run it. So it's going to run it from the top cell to the bottom cell. It's going to run all the cells. And we saw that notebook already. It just writes the surf reports. And the other notebook here is the one that's writing our the predictions of the swell heights. And if we go through, it's doing the same thing. You can run in backfill mode. We have some backfill data, or it'll go to the website and download the latest. And this is where it's going to, and it's downloading the latest predictions at the buoy that we're interested in. And there's a little bit more work of feature engineering in here, you can see, to actually create the features. But all it's doing in the end is it has this data frame df2 with the predictions that we're going to write to the feature store. So we just get the reference to this swells exploded feature group, and then we can insert it. Now, yeah, okay, so let's go back. And then finally, we have the two more notebooks. One is the training pipeline, which I can show briefly. So the training pipeline is going to go, you can see we have these transformation functions we talked about already. And there's quite a lot of features, because in this case we have not just the height, period, and direction, but for every hour that we're predicting. And I think in this case we have 168 hours that we're predicting. So it's quite a lot, and multiply that by 3 features. So it's 168 multiplied by 3 features. So it's quite a lot of features. But basically what happens here is we're creating the feature group by selecting the features we want to use. And then we get training data from the platform. We're creating training data, and then we're training a model. In this case, the model is going to be just a k-nearest neighbors classifier. So a very simple model. And then we compute the accuracy of the model, or the performance of the model, and we can just show you the predicted surf heights. And then finally, we're going to register that model with Hopsworks, because we want to use that model in our inference pipeline. So the last part is the inference pipeline, or the batch prediction pipeline. And what this pipeline does is it basically connects to the feature store, gets the model and downloads it, and then it gets a reference to the feature view, gets the latest feature vector, so the latest observation of the latest predictions. You can see all these predictions are the predictions of the swell heights. There's 119 of them for 119 different hours in the future. So it starts at hour 0 and goes to hour 2, hour 4, all the way up to hour 338, which is about 2 weeks. And then what it does, these are all the swell height predictions over those hours. And then what it does is it uses the model then to predict the surf height at all of those hours. So we get back a data frame, and yeah, it's just giving me a little warning there for all of those 119 rows. And then we're going to actually do 2 things in our batch prediction. One is we're going to write the predictions back to the feature store, because we said we want to understand the predictions and see what's happened. And then secondly, we're going to output this image with the predicted surf heights. And all it's doing here is just writing the image locally to disk. So if you want to look briefly at the action for that, so this is the swell predict action. This particular action actually does 2 things. It both runs the swell predictions feature pipeline and the batch prediction, predicting the surf height. So it's doing both of those. And this is the YAML file. This is the GitHub action. You can see it runs. I think typically it runs twice a day. But it's running this script, which will run those 2 pipelines, and then it's pushing the image with the prediction back into my main branch where GitHub Pages shows it. So this is the latest Lahinch PNG file, and that's basically what's going to be output on the GitHub Pages example. Okay, so let's have a look at the feature store. This is the last thing we're going to look at. This is Hopsworks feature store. You can go to app.hopsworks.ai to register. There's a bunch of new tutorials here to get started with. So I would recommend, there's logging me in here again. So I'd recommend running this Colab notebook. It'll create some features for you for a fraud model. And then you'll be able to, see the features created in these feature groups and inspect your data and make sure it works and try it out. It actually also will train a model and use deploy a model for predictions. So these are the feature groups that were created. If we, you can see you have a bunch of different ones there from different projects as well. And for Lahinch, you can see this is the wave heights. You can see we've got the observation time, the max height, min height, and wave height. We can get a preview of the data, which is kind of nice. You can see, okay, this is only online, but in the offline, we have more historical data. And you can see this is the historical data going back to 2004. And you can get statistics over this to get, to do some EDA. So we can see, for example, that the wave heights kind of follow this distribution. We can see, you can see there's look like that. You can see the activity in your feature group. So, job was run to ingest data. We can see also the great expectations rules. So I think there's one on this. There is one on this feature group here. We move down. Yeah, so these are great expectation rules. You can see that they're all running 100% success so far. You can get more results, and you can then tag these features for search and governance reasons. The feature view itself, the feature views, you can see there's a bunch of them. This is the one for this particular project, the Lahinch Surf feature group. And we can see also that there's a lot of features in here because we have that for all of the hours. Sorry, my internet's a bit sketchy here. And you can also create training data in here. You can see you can create new training data, but typically we do that from a program. And then finally, the models, we can see the models get stored in here. So this is my CJ Surf model. And I got 2 different versions of it, and we can see one of them is being deployed here. So the latest one is version 3. We can have a look at that. And you can see I stored some metrics with the model, so I understand its performance. Not great. And then the model, if I'm running a model serving, we can see it available here as a deployment. And you can see I have a bunch of models. This one's not currently running, but you can just press start to start them running. The reason why this one's not currently running is because the example I'm just running it as a batch prediction. It's not actually, this is a deployment, this is an online model. So this example actually works both as online and as batch, but the production one I'm running as batch because it doesn't need to be available 24/7. Okay, that's basically the quick demo. I'd like to just finish by reminding you that you can register at Hopsworks AI to create an account. It's free. You get very generous tier, free forever, like in the sense that it's time unlimited. If you want to store more data, or if you want to store data in your own cloud account, please reach out to us. We have a managed version that runs in your own account.